Uh, I will present my project entitled Syngas conversion into higher alcohols over K-modified compost catalyst supports on graphene-nanosheet coating alumina and carbon containing materials. The main objective of this research is to study the catalytic performance of K-compost catalyst regarding higher alcohol synthesis from syngas and study the effect of different types of supports, such as alumina, carbon-covered alumina, and graphene-coated alumina, and also use different types of activated carbon powder, commercial activated carbon, and fiber commercial activated carbons. To present the project, I will talk in three main sections. The first one is the K-compost catalyst supports on alumina covered by carbons. Secondly, I will talk about the K-compost catalyst supports on different activated carbons, and then study the effect of porosity and acidity of the catalyst on the catalytic activity of higher alcohol synthesis from syngas. As we know, the biomass is one of the important alternative energy resources, and syngas as the carbon monoxide and hydrogen produced from biomass, coal, and natural gas by three main steps. The first one is gasification, stream reforming, and partial oxidation. The most important benefits of syngas, is preparing of methanol and dimethylamine based on different heterogeneous catalysts, and it's called methanol conversion. Also, it can produce alcohols from C1 to C6, and the process is called higher alcohol synthesis. And also prepare long hydrocarbons based on Fischer-Tropsch synthesis heterogeneous catalyst. The produced materials from higher alcohol synthesis and Fischer-Tropsch synthesis can be used as octane number improvers, and also can use directly in cooperative fuel research engine and internal combustion engine as a fuel. Transition metal sulfide catalyst shows a very interesting results in higher alcohol synthesis from syngas. Transition metal sulfide catalyst also has promoted by second transitional metal like cobalt, nickel, ferrous, because cobalt when it's combined with molybdenum sulfide works as electron density acceptors on the S edge of molybdenum sulfide, which promote higher alcohol synthesis and also decrease the absorption of hydride hydrogen. Unmodified molybdenum sulfide catalysts produce mainly hydrocarbons, but when modified the catalyst by potassium inserts between the molybdenum sulfide crystallites and increase the selectivity to alcohol. So the potassium shifts the selectivity from hydrocarbons to alcohols. My research group has suggested the reaction network of the syngas conversion based on K-compost catalyst. And here the reactions including a lot of intermediate compounds, starting from the insertion of carbon monoxide on the promoter atom cobalt here in the way of unpromoted molybdenum sulfide catalyst, and in the way of promoted molybdenum sulfide catalyst upon receive alcohols and alkyne. The interaction between the support and active phase play an important role on the catalytic performance. In the case of the molybdenum sulfide crystallites, we have different sites for each performance. For preparation of alcohols, the reactions will be on the edge and the basals of the crystallites, but hydrocarbons inform in rim sites of the crystallites. In the case of weak interaction between the active phase and the carrier, so the stacking number will be higher, as you see here. and the stacking number have a positive correlation with the catalytic activity. Also, in the case of strong interaction between carrier and the active phase, the rim sites will be higher, and also it have a negative correlation because the rim sites responsible for hydrocarbon production, not alcohol production. And also, the slab length and stacking number have a correlation with the higher alcohol synthesis performance. In this project, we use different types of support. Firstly, we use alumina as a support for K-COMOS catalyst, and we cover it alumina by carbon type pyrolysis process and produce CCA. And also, we cover it alumina by graphene-nanosheets prepared by soil gel procedure. And also, we use different types of commercial activated carbon, powder activated carbon such as AG3, BAO, OBC1, and DAS. And also, we use fiber activated carbon, ANM, and TCA. Here is the picture characteristics: total surface area, total pore volume, surface of microburst is different, and we will discuss it to interpret the catalytic activity depends on the textural characteristics of supports and others. Firstly, we will talk about the catalytic performance of K-COMOS catalyst supports on alumina, CCA, and graphene coated alumina. The slide shows the catalytic activity the slide shows the surface morphology of the catalyst supports on alumina, CCA, and AG3. This is supports, and here the surface morphology of the catalyst after witness impregnation. It's characterized by scan electron microscopy, and as we know, the surface of the alumina is almost smoothly. Here also the morphology of the catalyst supports on alumina, CCA, and graphene coated alumina, characterized by transition electron microscopy, and the slabs of molybdenum disulfide as observed clearly as strand-like rings in multiple particles, as you see here in the case of catalyst supports on alumina, and here for CCA and graphene coated alumina. Qualitatively, you can see that the stacking number of the molybdenum sulfide crystallite increased after covering by carbon using pyrolysis process, and also after covered by graphene nanosheets. So the catalyst has been tested on fixed bed reactor at the temperature between 300 to 360. The pressure it was 50 bar, and the time of reaction is about 16 hours. As we see here, positive correlation has been observed between the temperature of reaction and the CO conversion. And also the catalyst, the CO conversion of graphene coated alumina were found to be higher than CCA and higher than alumina. And when we analyze the liquid products, liquid and gaseous product, which we got it from the reaction, as we see here, the main product was ethanol, propanol, and methanol, and the amount of alcohol comparing to hydrocarbons is sorry, is almost higher. Ethanol was the main product with the highest yield percent, and regarding the using supports, graphene coated alumina were found to be the best comparing with carbon covered alumina and comparing with alumina. And when we calculate the yield ratio between alcohol and hydrocarbons, also graphene coated alumina is higher than CCA and alumina. We interpret these results because the graphene take place between the alumina and K-COMOS active phase, decrease the interaction between them, which is decrease the absorption of hydride hydrogen and promotes the production of alcohol. So also previously we optimized the exactly weight percent of carbon in CCA, and we found that regarding to CO conversions, the optimum weight percent of carbon in CCA it's about 1.5, and for yield ratio between alcohol and hydrocarbons is in almost 1. And here also regarding the graphene nanosheets, also we found it it's the same results. It's about between 1 to 1.2. It is the optimum weight percent of graphene and CCA in graphene coated aluminum and carbon coated aluminum. In the second part of my presentation, I will talk about the effect of different activated carbon, powder and fiber activated carbon. Here, as I told you, we use 4 types of powder activated carbon: AG3, BAW, gas, and OPC. Here, the surface morphology characterized by scan electron microscopy for the supports, and here for the catalyst. For graphene, for AG3, it's formed by typical activated carbons as pore structure covered by fine layer of carbon, and also the PAW formed like microchannel structure. And here we can observe also the crystallites of K-comos after witness impregnation. The morphology of the catalyst is also characterized qualitatively and quantitatively by transition electron microscopy, and the slabs, as you see here, is appear as the friendly structure. Regarding the fiber material, we use ANM and TCA as the commercial fiber activated carbon as a support for K-comos catalyst. And as we see, is formed as a tangle fragments, and the tangle, but ANM is more tangled comparing with TCA. That led to form more tangled slabs of molybdenum sulfide comparing with, in the case of ANM, is more tangled comparing with TCA, and the tangled slabs produce more angles, which is suitable for preparation of alcohols, but the linear slabs which form from TCA produce more rim size, and also the rim size, as I explained earlier, is responsible for production of hydrocarbons. And the catalytic performance also for CO conversion, we can observe ANM is higher comparing with TCA. I explained it in the previous slide, and also the powder activated carbons is show almost better results comparing with TCA. Regarding the alcohol yield, we found that the PAW is the highest yield with in ethanol, methanol, propanol, which were the highest yield percent comparing with others alcohol. And we explain the good characteristics of PAW comparing with other activated carbon by distribution of the active phase inside the pores of the carrier, and also by the catalyst acidity, and also we explain it by the forming active phase quantitatively characterized by transition electron microscopy. Here, the figure shows the relationship between the textural characteristics and the acidity of the catalyst. When the surface area of microporous structure increases, the acidity is decreased. And also here, when the surface area of mesoporous increase, when the acidity of increase, the surface area of mesoporous increase. And this figure show the acidity of the carrier and the acidity of the catalyst, and we found negative correlation between the acidity and the CO conversion. When the acidity of the catalyst increased, the CO conversion decreased. So the highest acidity is the lowest CO conversion. Here also, we found positive correlation with the surface area of microporous structure and CO conversion. When the surface area of microporous structure increased, the CO conversion increased, and also in the case of volume of microporous structure, but opposite trends has been observed with mesoporous structures. And here also we can find in the 3D plots the dependence of CO conversion on the volume of mesoporous and the surface area of microporous and mesoporous structure, and we can observe that in the case of volume of mesoporous, it grows fast, it grows essentially faster than on surface area of mesoporous structure, and the following change of CO conversion against microporous and mesoporous surface area and volume look similar in A and B plots. And the differences between the alumina and CCA, I already discussed it in the previous slides. Here also the dependence of alcohol yield on microporous specific surface area and pore volume. When the surface area of microporous structure increased, the yield of alcohol also increased, and when the volume of microporous structure increased, also the yield of alcohol increased, and opposite in the case of mesoporous structure. So from here we can say that the catalyst that have higher microporous structure is more active than the catalyst with mesoporous structure in the case of Kekomos catalysts for higher alcohol synthesis from syngas. Also, we observe that the linear alcohols like methanol, ethanol, propanol 1, and butanol 1 have a positive correlation with surface area of microporous structure, opposite to isoalcohol like isobutanol, isoamyl alcohol. It's have a negative correlation with microporous structure. So when the surface area of microporous structure increase, the yield of ethanol increase, the yield of propanol increase, the yield of butanol increase, but the yield of isoalcohol decrease. Also in the case of volume of microporous structure, and opposite trends in the case of the mesoporous structure, and we explain that by the acidity of the catalyst, because the acid size on the catalyst is promote the isomerizations and increase the iso of alcohols. In conclusion, we can say that the supporting efficiency of alumina defenses of alcohol from Syngas over Kekomos catalyst has been improved after coating by amorphous carbon and graphene-nanosheet, because the carbon materials take place between the active phase of the catalyst and between the active phase of the catalyst and the supports, and decrease the interaction between them, and also decrease adsorption of hydride, hydrogen, and hydrogenous flavor. And different types of activated carbon has been tested, and the effect of texture characteristics on the catalytic performance also has been studied, and we found that unusual correlation between the catalytic activity and textural characteristics. For microporous catalysts show better catalytic activity comparing to mesoporous catalysts, and we interpret these results by the distribution of the active phase inside the pores, and also by the catalytic acidity. Finally, I would like to acknowledge my research group, which helped me to perform this project from Genesis Institute of Organic Chemistry in Moscow, Vladimir Maxime, Victor Dorkov, and Victor Kogan, and my colleagues from Lublin University, Professor Tatiana Shishko and Sepol Fikko. This project has been supported by Russian Foundation for Basic Research and National Research Foundation from South Africa. Thank you for your attention. I will come for any questions.